Welcome to this Forge College Explainer. I'm so glad you're here. Today, we're really rolling up our sleeves to tackle a completely crucial step in your Web3 development journey. If you've been following along with the track, you know we're in the business of building absolutely bulletproof Solana programs. And today, we're focusing on exactly how to harden those programs against bad data right at the front door. Let's get into it.
So you might be wondering, why do Solana programs sometimes just panic and crash? Think of your program like a super exclusive VIP club. In our previous lesson, implementing Borsh serialization for entry data, we hired a highly sensitive VIP host named Borsh. Now, Borsh is fantastic at reading the guest list when everything is perfectly formatted. But if someone hands Borsh a malformed ID card or, bad instruction data, Borsh doesn't just politely turn them away. No way. Borsh throws a totally ambiguous error tantrum and shuts down the entire line. We really need to fix that.
Just to map out exactly where we are, we're currently deep into the Programming with Solana track, specifically tackling the capstone module for building entry points. Our big mission for today is to hire a bouncer to stand right in front of our VIP host, Borsh. We need this bouncer to catch all that bad data at the door before we ever start letting real client interactions inside.
Here is our technical blueprint for today. We'll be going over 1. The entry point problem, 2. Building a debug helper, 3. The 4-step workflow, 4. Adding guards, 5. The debug report, and finally, 6. Next steps. By the end, you'll have a hardened capstone artifact that absolutely won't buckle under pressure.
All right, let's kick things off with Section 1, the entry point problem.
Here is the core issue. When bad data hits Borsh unprepared, you get a Borsh panic. The whole program just crashes. You get this terrifying, ambiguous error, the logs are a complete mess, your client has zero idea what went wrong, and it is literally just total chaos on the blockchain. But if we handle it correctly, we get an actionable diagnostic. A clean, stable string that tells our tests exactly what went wrong, keeping everything running smoothly and predictably. Much better, right?
Moving right along to Section 2, building a debug helper.
To get that beautiful, actionable diagnostic, we need a debug module that catches parsing failures right before they turn into those full-blown panics. Our debug helper acts exactly like our VIP Club's incident logger. First, it attempts a try from slice on the incoming byte data. If it fails, instead of freaking out and panicking, it gracefully catches the error. Then, it formats a stable diagnostic string containing the raw Borsh error, the actual byte length it received, and a conservative estimate of the expected minimum length. It basically converts Borsh's tantrum into a calm, informative message that our test suite can actually use.
Now I want you to meet the 3 shady characters usually trying to sneak into our program. First up, unexpected EOF. This is an input that is simply way too short. For this, you should check the length and variable length fields. Second, invalid enum discriminant. This means the discriminant byte doesn't match any known instruction. You want to confirm your discriminant assignment and your client-side encoding. And finally, invalid variant. This means the instruction exists, sure, but the nested struct inside is malformed. You'll need to carefully inspect your struct boundaries here.
Next is Section 3, the 4-step workflow of reproduce, isolate, fix, and verify. This right here is the highly systematic bouncer training program. It's the core workflow that turns a fragile entry point into a hardened capstone artifact. Step 1, reproduce parsing failures. Step 2, isolate the root cause. Step 3, apply minimal targeted fixes. And Step 4, verify with regression tests. Let me tell you, if you master this loop, you are going to save yourself countless hours of headaches during your Web3 career.
The absolute most crucial point in Step 1 is to purposefully break things. You actually need to craft a unit test with a deliberately truncated instruction payload, something like a vector with just a single 0 byte. We are deliberately handing our program a fake ID, just to capture that diagnostic output from our helper and prove that the failure is entirely reproducible in a controlled test environment.
Which brings us to Section 4, adding entry point guards.
Okay, so we've reproduced the error in testing. Now it's time to station the actual bouncers at the door. An entry point guard is simply a cheap, deterministic check for length, discriminant, and version. It happens right at the door, before we ever attempt that super expensive full Borsh deserialization. It's exactly like the bouncer checking IDs and making sure there's cover charge money before we ever bother the VIP host. It saves computation and, most importantly, prevents messy crashes.
By adding these cheap guards right at the top of your process instruction function, you isolate the root cause and catch bad data early. Then, you just return a standard invalid instruction data error. Boom! We avoid those ambiguous Borsh panics entirely. We've effectively transformed a catastrophic crash into a clean, polite, and totally expected rejection.
Let's actually look at the checkpoint criteria to prove our guards are working the way we want. Before the fix, handing it a truncated payload gave us an unexpected EOF panic. But after the fix, it's cleanly rejected by our length guard with an invalid instruction data error. Same thing for an invalid discriminant. It used to cause a massive deserialization panic. Now, the discriminant guard rejects it instantly. It is literally a night and day difference in how our program handles bad input.
Once you've applied those guards, you hit step 4, verify. You simply run cargo test. This step catches regressions and ensures all your local tests pass cleanly. It's essentially checking all the doors and windows to make sure absolutely no new bugs snuck through the back door while we were busy installing the bouncer at the front.
Next up, Section 5, creating the debug report. This is the climax of this lab. We're compiling the ultimate incident log to submit to your Capstone repository. Your debug report is the hard proof that your entry point is truly robust, so it absolutely must contain these specific artifacts: the failing input bytes you crafted, the observed error string from the debug helper, a short root cause diagnosis, the exact code change you applied, like adding a length guard, and the regression test evidence proving the fix worked. Remember, this document is a critical deliverable for your Capstone project.
Finally, Section 6, Capstone Next Steps. So, how does all this debugging prep us for the finish line? Well, up next, we'll be integrating client interaction stubs. The diagnostic tools and regression tests you've built today are going to be completely invaluable when we start pushing real, networked client interactions into our program in the next lesson. Thank you so much for joining me for this Forge College Explainer. Do me a favor and head over to forge.college to access even more educational resources. But before you go, I want you to ask yourself this. If a single missing byte can crash a multi-million-dollar protocol, what other silent vulnerabilities are waiting at the front door of your smart contracts? Really think about that. I'll see you in the next one.